Okay, so today I'm going to kind of do something a little bit different. So in this session, I'm going to kind of do a more of a real life example. Obviously, for the students that are on the fluid viscous dampers project, this is a model that you're probably familiar with. Let me actually bring up the model here real quick. For other people, maybe not. So I'm going to try to go through, take a few minutes and just kind of describe what the project is, and then kind of go through the simulation that I ran on this, and go through how I set that up and kind of why I've set it up that way. Again, it's not the only way to set it up, but just kind of looking at a few of the different, things I was looking at. So this should be kind of this should kind of build on the pin connections, I think, from last time, and the frequency analysis as well. So this should be kind of more of a real life example, or kind of a research example that you might see. So this is the model so far. This is a project of, or this is a model, I'll say a simplified model of a building. And what this building will be tested for is it's going to be tested along the Z direction, which is this direction, for a vibration from an earthquake. And we're going to try to figure out what kind of effects that has. And if you notice all these brackets here, so there's going to actually be two different types of this model. There's going to be the model with these brackets, and then eventually these brackets are going to be replaced with dampers to try to damp out the vibration. And then the two models will be analyzed and try to figure out what kind of effect the dampers have. Hopefully, the dampers help the model. But that's kind of the general um, kind of goal of this project. So obviously from here, the base is going to be kind of fixed. And I'm going to go through, for today, I'm going to kind of go through setting up a frequency analysis for this model. I have some other analyses here as well, but I'm just going to start a new one and kind of go from scratch. Because it's one thing I've noticed, it's one thing kind of just doing a very simplified frequency analysis or very simple static analysis. But when you have something a little bit more complicated like this, it can get a little bit confusing. So hopefully today's session will kind of help with that. So first thing I'll do is, let me stop here for a second. Any questions or anything about this project or kind of the goals, or kind of what this building is going to kind of be undergoing or anything before we get started? Okay. So, so the goal here is obviously I'm going to start with a frequency analysis. Again, since we're only really trying to analyze it in the Z direction, which is going to be the direction parallel with this face here. Um, we don't really want to have a lot of movement. We don't actually want to have any movement going other ways. Again, so there's going to be, and when you're dealing with a complex analysis like this, sometimes you do have to go through and kind of simplify certain things. And again, this is not probably going to be the final analysis on this project. This is just more of a preliminary analysis. But it never hurts when you're starting off with an analysis, just to kind of go through and try to simplify it as much as you can, just to see if you're getting the behavior you're expecting. So you'll see a few things like that today. So I'll kind of try to go through where the model has been simplified or where the analysis, I would say the model is technically the same, but where kind of simplifications in the actual analysis were made. So the first thing I'm going to do, I'm going to obviously kind of start off with a frequency analysis here. So I'll just start a new study, and I'll just go under frequency here, and I'll just leave this named as frequency 4 for now. Um, so we've got that for now, and then what I'll do is let's go ahead and just accept. So obviously, this should look rather familiar from last week when we did the frequency analysis. So for the frequency analysis, I think I mentioned also last week, so before we get started, there's a couple things that are different for a frequency analysis versus a static analysis. One thing is there is no, for our contact conditions, if I go under our interactions and go to our global interaction, if you notice there is no contact condition here. There's only bonded or free. So this is something that you have to kind of be mindful of when you're doing a frequency analysis. So if you have this really complex context problem that you set up for a static analysis and you're trying to do a frequency analysis on it, those contexts are not actually supported in a frequency analysis. You'll have to kind of think about a different way of actually restraining them to kind of achieve that. So the first thing here, obviously all of these plates, I'll go back to the model a little bit. These platforms here are designed to be 3D printed out of PLA. The material for these in the study is actually made out of ABS. That's just because SolidWorks doesn't have last time I checked, doesn't have a good profile for PLA or good material for PLA. ABS has similar material properties. It's not identical. But if you're going for a high degree of accuracy, you'd probably set up a custom material based on whatever filament or whatever was used. So these are obviously ABS in the study, but they will be printed out of PLA or PETG or something similar. These frames are made out of steel of some variety. We're still trying to figure out the exact grade of steel. For now, I just made these out of plain carbon steel, which is probably you've probably seen that a lot in SolidWorks. That's just one of the default steel materials. Um, Also, there are these little washers here as well, just because to kind of fill in this gap that are also made out of the same material as these frames. So that's kind of the thing. So when we're looking here, obviously there's no hardware right now. So what we're going to do is in this study, we really don't need hardware, but we're going to have, talking about our pin constraints, we're going to have pin constraints going through all of these joints here, or pin connections. And I'm going to go through kind of how to define those. Again, it's going to be very similar to last week, I believe it was, but it's a little bit, when you're dealing with like a lot of pin connections, it can get a little tedious. So I'll kind of go through a couple of different strategies of kind of how to apply them and keep them a little bit simplified. So one thing here, obviously, since all of these frames are actually in contact, so this face of this frame is actually coincident or coplanar with this back face. If I can get in there, with this back face of the back frame. So in this case, I really don't want a bonded component interaction, because if it's bonded, literally everything is just going to be like it was welded or fused together, which is not really what I want. I want to actually be able to get some motion here, and I want the pins to actually be the connecting factor between all of these different components. So I'm going to just go and switch this over to free. By making this free, though, I am making putting quite a few more degrees of freedom in this system, and I'm going to have to actually constrain it a little bit better as well, because there's going to be a lot more flexibility or a lot more areas that can move. So I'm going to have to be, cognizant of that. So we'll do that. I'll go to free and I'll go and hit accept. So these are global free interaction. Any questions so far? Okay. So the next thing is obviously our fixture. So I'll go down here kind of in order. Obviously parts, we've got quite a bit of parts here. Actually, I'll start actually at parts. So we've got all of our frames. So we've got quite a few of them. And so a couple of things I'm going to want to do here is for our floors, since they are ABS, and to kind of simplify the analysis, again, I'm getting a little bit further away from realistic, but it never hurts when you're doing a preliminary analysis like this. Try to simplify a few things. So instead of having these floors be flexible where they can actually deflect and deform, I'm going to actually just take these, I'm just holding shift here, selecting all of these. I'm going to make them rigid, which just means like from statics or strength of materials, meaning there's no deformation. Again, it's not very realistic, but we're really more concerned with kind of the frames and how the frames are actually vibrating versus the floors. At a later date, we can always come back and do the floors, but it never hurts. And if you notice, when you switch these to rigid, this little symbol goes from like looks like a deflected or deformed body to like a solid rigid body. So it's just a perfect cube, it looks like. So that's one way of doing this to kind of simplify things a little bit. Another thing is also I will actually go through and then there was an issue that I was running into with the washers. I'm going to run the analysis with the washers not being rigid at first, and then I'll kind of show what kind of issue that kind of created. And then after that, I'll go and actually go back and make the washers rigid just to try to eliminate that. So that's the first thing. So make those components rigid. Again, there are so many different ways you could set up this analysis. This is just one. So I'm not saying that this is the only right way. I'm not even saying this is a correct way. Obviously, by making stuff rigid, you're kind of getting a little bit more unrealistic, but it never hurts when you're doing preliminary analysis or analyses to kind of try to simplify and just kind of make it more complex step by step versus just going really, really complex. And then you may have several issues that you have to try to solve. So that's definitely a way to kind of start off. So the first thing is obviously those are rigid. Then after that, next thing, let's go down to fixtures. Again, remember for a frequency analysis, I do not need any loads. So I could put a load if I wanted to, but in this case, technically the only load would just be the weight of the building itself. So I'm not going to put any loads, but I will go ahead and put a fixed constraint on the bottom face here to kind of simulate that being attached to the ground. So what I'll do here is we'll go to fixtures, we'll go to fixed geometry, and we'll go and put a fixed constraint right here. So we'll go and do that. And so there's our fixed constraint. Obviously for loads, I'm not going to really worry about loads too much. But now getting back to our component interactions, or rather our connections, now it's time to actually go through and put all of our pin constraints. This is probably going to be one of the longer portions of this analysis, just putting in all the pin constraints. Because in SolidWorks, there isn't really a way to actually, I mean, I wouldn't say there's no really way to mirror or pattern component interactions. It's something because each one is defining different components, something you really have to kind of do manually for each different one. So it can kind of get a little bit tedious doing that, but there's, you know, it never hurts to be extra careful because if one of your pin connections are incorrect or something, then the behavior of the model is probably not going to be exactly what you're expecting. So I'm going to do, so let's go under connections here, and then let's go to a pin connection. So this should be somewhat familiar from last week. So the first thing we'll do is I'll just keep it at the default. I'll keep it with a retaining ring, no translation, which just means that these components can't actually come out, but I'm going to go back later and do some other things that'll prevent that as well, just as another measure to make sure that these, because obviously you want to make sure that this entire system only pretty much moves along the Z direction. So it's kind of swaying this way, kind of back and forth. Again, that's not 100% realistic, but if we're trying to analyze in one direction, it never hurts again to start with a simplified representation and kind of see what behavior we're getting before we start, getting into maybe adding more degrees of freedom and seeing how the structure behaves that way. So the first thing we're going to do here is start with our pin connections. So for our pin connections, what we can do is one thing that's actually really nice. So I'll start off with the pin connections here. So for pin connections, obviously, I think last time I think we actually did it between three concentric faces. You can obviously do it between many concentric faces if you need to. So what I'm going to do is I'm just going to select obviously this face, which is the face of the washer, the face of the inner frame, and then the face of the actual floor um, so that should put a pin connection between all of those. Um, so that's really kind of nice that you can do that with pin connection. You don't have to necessarily go face to go one face to one face, that face to the other face as separate ones. You can run them all at the same time as we kind of saw last week. So one thing here, since I've got a lot of these to put in, I've got one here, one here, one here, there. I've got them all over the place. I'm gonna actually a trick here is actually to pin or keep visible this menu here. Um, so what that'll allow me to do is after I hit the green check here, it's going to put a pin here, but it's going to keep this dialog open so I don't have to launch it every time, which is really nice when, you've got a lot of, pins or different constraints to put in or connectors. So we'll go ahead and hit accept here. And let's see if let's actually see, we should actually have, let's make sure that, uh, let's make sure that pin's actually, oh, there it is. Okay, so I'm going to delete that one more time. So one thing, you're not going to see the pins until after you actually, um, exit out of it. So yeah, so we'll do this and we'll go back in here real quick. So let's go back to our connections. Let's go to pin. Okay, so again, go and pin this, and then we're gonna do select all four of these. Another thing also, if you look at my mouse, you'll see that there's a little mouse icon with a green check in the on the right mouse button. So I can actually just right click that and that'll automatically accept this connection or whatever I'm trying to do. This also works with features if you've noticed for extrude, revolve, stuff like that. So it's a quick way that I don't have to go all the way up and try to hit the green check. I can just right click, which is really nice. So it'll do that. So this one is already there. One thing is when you're doing this, you're not going to really see a lot of, it's not going to give you a lot of feedback until you actually exit out of the feature. So I'm just trying to so it's a good idea is to keep track mentally of where you're putting these pin connections. So I'm going to kind of go through, obviously here we only have two faces, so we'll go here, right click, do the same here. And I'll kind of just work my way around here. So again, it doesn't really matter which order we select them in. I'm just going to try to do, one thing I will try to do is do layer or do level by level. So I'll try to keep all of these in one, kind of in one group, and you'll kind of see what groups after I accept this, and then do this in another set of groups. So then if there's ever a problem with one set of groups, I don't have to look through all the pin connections. I can just kind of go to that group and look at them. It makes it a little bit easier to kind of sort out problems if there are any. So next I'll go here, 1, 2, right click, and then we'll go here, 1, 2, 3, 4, right click. Yeah, same here. And we'll go and rotate around to here. And then here, 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 here. Like I said, this is kind of a tedious part of the analysis. One thing, if you go away by accident and you don't have that green check anymore, you can just always hit the green check here, which does the same thing. So this is where pin connections can get a little bit fun. So then we'll go here. We'll try to go through this as quick as possible because it's gonna obviously probably you guys don't want to have to see the same thing done um, 500 times. It's actually not that bad, but it kind of feels that way. So we'll do those, and then that should be this entire level here. So now I'll go ahead and unpin and then hit the red X, which means I'm not adding any more. If I hit the green check, it's going to give me an error because I don't have any faces selected. So I'll hit the red X, and now I have all of these pins. And you can kind of see, then after that, the one thing I want to check is go through here, make sure all the pins are where they should be, make sure I'm not missing any. So those look pretty good. I do have this pin group 1 that I had before. I'm just going to delete that. So by default, when it does a SolidWorks simulation starts doing groups of connectors, it'll try to just make these groups like this. So I'm going to try to keep them in their own thing. So I'm going to rename this just by slow double clicking to pin group 1. And so again, that's why it's really useful because now I have all of these under one folder. The next will be under the same, and then so on and so forth. So if I have an issue, I can kind of just look at this one folder versus having to look at, because even this one folder has quite a few. It's got, what is it, 3 on each side. So it should be have 12 of them. So it's just a good way to, kind of keep them sorted. So we've got that. Okay, so we'll have this, and I'll go and hide this real quick, and then we'll launch the pin connection tool again. So we'll go here. And then we'll do something very similar. So I'll go and pin, and we'll start on this level here. So we'll go here, 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 there. And some part of while I'm doing this, part of the challenge of sometimes these really, I wouldn't say this is a very complex study, but when you have a study with a lot of components, you have a lot of contacts, it's not necessarily a hard thing to do, but it's really easy to kind of lose track of where you are and what you've done so far. So that's kind of one of the things to kind of keep in mind, just to make sure that everything is actually, you're defining everything the way you want, and you're not missing any faces or missing any areas where you want pins. So we'll go here. But definitely the right-click method does save quite a bit of time when you're doing stuff like this. And also along with pinning the dialog open. So we'll do this. And that should be it for that one. So again, we'll do the same thing. We'll do this and we'll do that. Okay, again, go around and check, make sure those are all there. And now we've got our pin group 2. So you can kind of see what we're doing. We should end up with 4 pin groups. So 1, 2, 3, and 4. So we'll do something very similar now. Again, go up to connections, go to pin. And we'll go again. Can pin, no pun intended on the, pin the dialog, but, pin the pin connection dialog, I guess you could say. Um, so then we'll go here and start again. You go and move around here. Sometimes if you had an edge or something, you just unselect it and then click it again and hit accept. So then we'll go and rotate around. There's that, and one more set on this side. Okay, and on pin. Okay, go and check it again. This is a great place to save as well. Again, it never hurts to save every once in a while, especially sometimes you get, I know personally speaking, I'll kind of get sidetracked by putting all the connections and everything. And then if something were to happen, SolidWorks decides to crash or something, you end up losing your work. So it's always good to, especially between groups is a perfect place to go and save. So we have that, and let's add another group of connectors. And we'll do something very similar up here. And again, make sure this is pinned here. Oh, do I have something else? I still have something else selected. So you ever have something happen like this? Sometimes you have some ones that are still selected from last time. Right click here in the box, just do clear selections, and then we can kind of start over. It's giving that error because I have 2 cylindrical faces up here, and the other 2 were selected probably down here somewhere. So they're saying that it's hard to put a pin through, or it's impossible to put a pin through 2 sets of cylindrical faces that are not, concentric. So then we'll kind of start again and hopefully that'll fix that issue. So here, there we go. 1, 2, 3, 4. Okay, go and rotate around to the other side. Again, it doesn't really matter what order you do them in. I'm going in one direction, but you could go from the other direction. You could select them just as long as they're all selected. Doesn't really matter which order they're in. You just want to make sure that all the cylindrical faces that you want or all the faces you want are selected in that specific pin connection. So we'll do that. And last but not least, actually, it's not last but not least, we've got one more set. So we've got that, and then we've got these and this. Yeah, see, like there I kind of missed one, so then you can come back and just hit it. Hit accept. Okay, so we've got this, unpin, close, and make sure got all the pins. Let's go and save one more time. And this is a good time just to kind of look around, make sure the pins are looking the way you want. Make sure they're on all the different ones. So that looks pretty good. Let's go and collapse this as well. Any questions so far on pins or anything in this model? I know there's quite a few of them, but it's kind of the same process repeated over and over again. But anybody, does anyone have any questions? Okay. So we got our pin connections now. So that's kind of the first step. And again, one other thing for frequency analysis, if you notice, if you do go to connectors, there's actually no bolted connection either. So this is another difference. I think I also talked about this last week. In the static analysis, there you have the option for doing a bolted analysis or a bolted connection, where a frequency analysis or dynamic analysis will not have that option. So a good way to kind of do that is to, if you have some sort of bolt or something, again, you're not going to be able to simulate the exact same way you would simulate a bolt, but pin is kind of a good replacement, or it's an option for a replacement, I would say, um, to obviously be able to run this type of simulation. So the next thing, now that we have our pin connections all set up, the next thing is going to be to actually kind of make sure that this can only pretty much deflect in the Z direction. Now, the way I decided to go about this is to apply roller slider constraints to all of these faces here. So here, 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 pretty much all of them on both sides, just to obviously making sure it can still slide along that plane, but it's not going to be able to twist. It's not going to be able to come this way. Again, just to kind of simplify the analysis in this regard. So what will go here again, this is going to be a little bit tedious as well, kind of like the pin connection. So we'll go to fixtures now. Obviously, we have our fixed geometry, so now let's go ahead and do our roller slider. So for our roller slider, then pretty much what we'll do here is go here, 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 here. Now I'm selecting the outside of this instead of the inside. It doesn't really matter too much, but since this is rigid anyway, I just figured the outside would probably be a little bit easier to select, and sometimes it's as simple as that. Again, most of the deflection is going to be within that plane. It's not going to be deflecting out, or it shouldn't deflect out of plane. That's the whole reason for kind of doing these. Now what I am doing is I'm actually not selecting anything on the washer for now, since there's that pin connection and we had the we put that thing for no translation. That should mean that this washer should not be able to slide in and out. And a question you might also be asking, if the washer is not able to slide in and out, and by definition these frames should not be able to slide in and out, why do I need all of these roller slider constraints? Well, kind of the reason for that is just because it cannot slide in and out at this point does not mean that this cannot deflect in the middle. So this pretty much can end up looking like that or something like this instead of going here. So just because it's prevented from moving in and out or translating on this specific point here does not mean that the whole frame itself cannot deflect in that direction. So that's where the roller slider comes in. It's making sure that this entire face stays pretty much on plane. Um, Again, it's not going to be the most 100% realistic in real life, but it's good for kind of preliminary analysis where you're trying to kind of simplify as many things as you can. And again, the less things you have going on, the analysis should be shorter. It should not, take as much resources as well. So it's always good to kind of run something like that, and then we'll always come back and look and say, okay, what else can we do to maybe make it more accurate or something. So I'll continue going here. Obviously, the nice thing about these frames here is you can just select the entire frame. It goes all the way to the top, so I don't have to select that every time, obviously. So we're going to go here, and we'll keep working up here. So we've got that here, here, here. So these are a little bit quicker to add than the pin constraints because we're just selecting the faces. So that looks pretty good. Again, I don't really need to do much with um, I don't have to do much with this face here because it's rigid. If it wasn't rigid, then I might consider doing something here because then it could still deflect. But since I've got the pin constraint here, and obviously if it's constrained from translating in one point and the entire body is rigid, that should propagate everywhere. But if we're getting like results that don't make sense or something, we might have to go back and kind of modify that. But when I ran this study, I say last week sometime, that was actually working fine. So unless we run into something new, that should be sufficient. So we'll grab these and let's see, grab those. And this is where it's not necessarily hard doing this, but it's easy to kind of miss one. Again, it's helpful to kind of see the blue face. How it's been selected. Another reason it's kind of easy to do this on the outside, so it's a little bit easier to see. So we'll do that. And kind of rotate it around again. Just make sure everything, we got all of the components we want, all the faces we want. So it looks pretty good. So let's go ahead and hit accept here real quick. So now for our roller slider, obviously we've got a lot of fixture symbols here. So kind of recapping, we have a fixed constraint on this bottom face. Since this body is rigid, that means technically everything is fixed. The fixture will propagate everywhere because there's no deflection allowed. Then we have our pin connections at all of the corners or all of the areas where the members intersect. And then we have all of our roller sliders pretty much along all of these flat faces on the outside of these frames. Any questions so far?
Yeah, I know
Okay.
you place them on the outside,
Mhm.
just to keep them, from, when the simulation runs, it keeps it from, running out. But do you also need to apply those rollers inside of each frame on the other face so that it doesn't, you know, compress in a sense?
So that's actually a great question. I did actually think about that. So the reason I didn't actually apply it on the inside is so for a couple of reasons. So obviously on the outside, if this is prevented from moving outward, obviously this is not a rigid body, so it can still deflect. But if this can't move outward, it's gonna be kind of hard for the inside face to move out as well. Another reason for not putting them on the inside, if I were to put a roller slider on both sides, as this member were to deflect or try or vibrate or whatever, what would end up happening is the thickness of the member would not actually be able to change because of that roller slider, because this face cannot move off plane and the inside face cannot move off plane. So that again, that's what the issue kind of with that is. If you remember, probably from a previous session when I was talking about Poisson's ratio, where when you stretch a member, the member will actually, as it elongates, it'll get thinner in the other directions. By putting a roller slider on the inside as well, it's only really going to allow it to shrink in this direction here. It won't actually allow it to shrink here. Again, this is probably very, very minor for this specific study. But in this case, I don't think, like by fixing it or by putting a roller slider here, I think it gives the correct behavior without trying to simplify it anymore, if that kind of makes sense.
Yeah, that makes a
Um,
lot of sense. Thank you.
yeah, you're welcome. Yeah, so that was just something, but yeah, that was something I kind of considered and I was like looking at because it definitely sometimes, and this is where it kind of gets a little bit confusing also too, because sometimes you can go a little bit crazy with the fixtures. I know I fall into this trap occasionally as well, where it's just like you just start adding them everywhere, just in case type measure. So it never hurts to kind of, you know, add them as many places as you think, and worst case scenario, just run the study and see what the behavior is. And if you're getting something that's really outside of what you're expecting, then definitely go back and, then you can try to look at it, see the behavior it's giving you, and then try to kind of figure out, what can I do to stop this behavior from happening in this specific orientation or direction or whatever. And then you can always go back and change it. Again, with larger studies, that it kind of gets a little bit less appealing to do it that way. Because obviously it's one thing if a study takes, a minute or two. If maybe a study that's taking a half hour, an hour or something, or if you're running on like a slower computer, then sometimes it's, it's a little bit more appealing just to try to fix everything. But you should always try to kind of restrain away from doing that. Another trick that I will mention, kind of along those same lines, is when you're doing a study like this, obviously frequency analysis will take a bit more computational power than like a static analysis. So one thing you can also do is you could literally set up this study pretty much the exact same way with the pin connections, with the fixed, with the roller sliders and everything. And you can just go into static analysis, do this in a static analysis, and maybe go up here and just apply a force maybe in this direction or something. Obviously in the direction you're trying to analyze, and just run that study and kind of see if you're getting the behavior, because that study a lot of times will be quicker than a frequency analysis, because it's not having to calculate all different frequencies and things. So that's kind of another way that you can kind of, and this is something I actually did. I didn't actually show this today, but this is actually something I did starting out just to make sure that the connections were kind of working in the way I thought. So if I put a force here, I'm expecting this building to obviously only move in that direction. So if something else is moving in some other way, then I can definitely fix it right there. So that kind of helps to do maybe a simpler study, instead of the one you're actually wanting to do first, and then see if you're getting the correct behavior. Just animate it, see okay if it's moving there, make sure the pin connections are working, and none of the maybe make sure that none of the members are slipping out to make to confirm that the pins are actually constraining all of the faces there. Versus, let's say, sometimes if you miss an edge or something, maybe I missed, or sorry, not an edge, a face. If you miss a face, let's say on this member, everything else will be constrained, but then this won't be able to freely move up and down. So that's a great way to kind of check for those type of things. But if you have the time or whatever, and you just don't feel like doing another study, there's nothing really wrong with just doing it in a frequency analysis or whatever analysis you're trying to do, and just see, kind of see what the behavior is and kind of go from there. Any other questions or anything before we move on? Okay. So, so the next thing, so now at this point, um, we're pretty actually good on this study. So this is, we kind of look at the study. Obviously, we got our roller slider constraints. We've got our fixed. We've got our pins. So this really should be constrained enough to actually go and run our study now. Um, So it's obviously good to kind of look at everything. So obviously, usually another method to kind of look at to figure out if everything is fixed, or if everything is constrained properly, kind of a mental way of doing it, is start kind of from the bottom, or start wherever your fixture is, and try to figure out to make sure that everything is connected in some way to that fixture. Because obviously, if something's just floating around in space, that can obviously give a wide amount of problems. So kind of look from here. So we have our fixed constraint. Obviously, this body is rigid. Even if this body wasn't rigid, it wouldn't really matter too much. Then this body here is obviously connected by pins with all these members. Um, these members are obviously connected to these members with pins. So obviously the pins are going all the way up to there. So that pretty much connects the members together. And then to fix the issue of the, out of plane kind of deflection, then obviously we can look at our pin, or sorry, not our pin, our roller constraints. So So that's actually a really good way of kind of looking and just kind of getting a mental picture of what your structure looks like, what the system looks like with all of the fixtures, loads, connections, and et cetera. So okay, so now from here we should be good now to go and run create a mesh and try to run this study. So let's go here to mesh. Let's create a mesh. For now, I'll just leave the mesh kind of in the middle, just to kind of see. Again, later on, it's always good to maybe make the mesh a little finer. But for now, it's not a big deal, so we'll go ahead and just go ahead. Let me look at the mesh parameters here. We'll just use a curvature-based mesh. That's fine. You can also probably get away because most of the things here are actually, there's not really a lot of curvature here except for the holes. So you could probably also get away with a standard mesh here, but I'll just leave it at the default and go ahead and hit accept and have it create this mesh. Again, so since we've got an assembly here with quite a few components, so it's typical that it'll take a little while to create the mesh and everything. Okay, let's see. There we go. Okay, so one thing also, since this is probably the first time, I know it's the first time I think on these sessions I've talked about making something a rigid body. So rigid body is actually still meshed, but if you notice, rigid bodies are actually colored in orange, so that'll tell you that that's actually it's treated as a rigid body. So that's kind of good to also make sure everything's consistent, obviously. So make sure all of our frames are not rigid and make sure these are rigid because that's what we kind of defined. So this is another great way in the mesh to really just kind of check everything and make sure that um, everything is looking like expected. So go there. Again, this is not I mean, there's only one element across here. So again, for accuracy, it's probably not the best mesh, but it's great for just kind of a preliminary analysis. And then we can always, mesh is really, really easy to obviously make more fine later on. So we've got that. Any questions about the mesh or anything? Okay. So next, what we can do is we can actually just go ahead and run our study. Well, actually, before we run the study, one thing that I actually did not look at. So let's go up to our properties and just look at our kind of look at our the properties of the study here. Obviously, the frequency analysis, how many frequencies you want to calculate. You can calculate some other things, upper bound. Um, so in this case, since I think also the research we've done, I'll just the study a little bit differently this time than how I did it before. Before I just left it at the default and just kind of ran it. But I think from the research we've done for earthquakes, they're usually well below 20 hertz. So any frequency above that would probably not really matter as much. So what I might do here is maybe just do an upper bound, maybe doing like an upper bound of maybe let's say 40 hertz, just to give us a little bit of um, well, actually, let's see. Well, but then it disables. Actually, I'll just leave it at a number of frequencies. I thought you could do number of frequencies and that, but actually that would not work because obviously there's only a certain number of frequencies between this and this. Um, but you know what we can do? Yes, we'll just do. Yeah, actually, I'll try it this way. This is probably because you saw last week doing the number of frequencies. We'll do this. I'll actually up this to maybe let's up it to let's say maybe 60 hertz just to get an idea. So we've got our 60 hertz there, and we should be good. Everything else we really shouldn't need to do anything with. So we're going to hit OK, and this is another great time to save. And make sure you're in the graphics area when you try to save. Okay. I'll go ahead and save real quick. And then what we'll do is go ahead and just run the study. And give it a second. Okay. So the study should be running. Again, this will take a little bit longer than a static analysis or something like that. Again, you can't see the window that pops up. Um, but it'll obviously it's just saying solving is 23%. Actually, that actually ran rather fast. We're just waiting for the results now. Okay. So the first thing, obviously we have our amplitudes. We only have two amplitudes that it's coming up with. Um, another thing here, obviously, this is the issue I was talking about earlier, with the washers doing this really, really weird type of behavior. I honestly don't know why these are kind of behaving this way. This is why what I actually ended up doing was going back and actually making all the washers rigid bodies, just to kind of avoid this kind of unwanted, effect. So that's kind of what it looks like. Let's look at our mode shapes here real quick. Um, so let's go here and let's go and animate our mode shapes. So we've got two mode shapes. This is another great way if you don't want to have to do a ton of frequencies. If you're only interested in a certain frequency range, then it's a great way to just to do um, just the pretty much what is it called? Just the range from 0 to whatever your maximum frequency is. Because if you don't really have a lot of high frequency vibrations, there's really no need to actually analyze all of those. So one thing before we look at our mode shapes, let's look here real quick and let's do list resonant frequency. Actually, sorry, not list resonant. Let's look at our list mass participation. Again, I want to look at and make sure that that mass participation in the z direction, which is the direction we're interested in, is above 80% or zero point 0.8, which it is. So obviously the mode shape 1, which is the weird thing with the washers, is like got extremely little mass participation. It's 6 e negative 12. So that's very, very small. And our mode shape 2, it has a very large, pretty much the entire mass, or not the entire mass, but the entire sum of the mass participation is pretty much coming from just this one here. The rest of this is just very, very, it's pretty much negligible. So by looking at this, we can pretty much tell that mode shape 1 is not our dominant mode in that direction anyway, actually pretty much in any direction. Um, but our mode shape 2 is going to be definitely dominant in the Z direction anyway. So now that we know that, let's go and animate this one just to see what the washers are really doing. Let's go ahead and stop this again, and always try to stop this and try to do like 15 frames per second. Again, if you have a slower computer, it's fine to just leave that at 5, but 5 I find to be a little bit kind of what's the word? Kind of choppy, I guess you could say. 15 is a little bit less choppy. Yeah, so this is what it's getting. So obviously, just by looking at this, it- yeah, I don't, in real life, you can kind of look at this and say this is not something that would really happen. So theoretically, yeah, if it vibrates, it could technically expand on a micro level. These washers could. Obviously, this is just an exaggerated deformation scale, obviously. But yeah, so that's not a really a big concern for us, especially since there's such low mass participation in this. So we'll kind of ignore that one for now, and we'll go over to amplitude 2. And so this is going to be obviously our dominant mode here. So let's go and animate this as well and kind of see what we're looking at. So again, we'll let it go. And you kind of see this is usually, I mean, like for earthquakes, this is the typically the motion you'll actually see. You'll see the building um, kind of swaying in kind of this way. So definitely, so this is going to be our predominant thing of the mode or predominant mode here. And you can see why there's so much mass participation because literally the entire, um, like all of the mass pretty much above here is pretty much moving. This mass is moving a little bit, but this mass is not, happening a lot. Obviously, the base is rigid, so that's not really going to obviously move either. So from there, and then again, another thing to check here is I'm looking at the pin connections, making sure that everything is um, working as I would expect. So you should have, pretty much, um, you should have rotation about all of these pins, and it should be transferring the forces or the vibration to all of these different things. Again, this amplitude, like we kind of talked about last week, is not really don't trust this for what your actual displacement is going to be in the model. This is really just showing how it's displacing if you were to, or not how it's displacing, what the amplitude would be and how it would look under a certain vibratory condition. Um, so these in real life for displacement really don't mean a whole lot unless you do another type of analysis, like a dynamic analysis, to actually apply loads and figure out what actually happens with everything. Okay, so we have those. Again, check these pins. Those look good. If these weren't correct or if these weren't acting correctly, what you end up seeing is a member like I'll try to go down here because that's going to give me a headache. Looking at that sway back and forth. So another thing you can look at here is if this wasn't actually constrained properly, or let's say this one wasn't constrained, you might see this member still moving back and forth, but this member here is actually just staying where it was, or it might be moving, but it's not going to be moving in sync with this one, with that pin. So those are the type of things you want to look at. But yeah, everything looks good. We see our members flexing, we see everything, so that's really, really good. Any questions about this analysis so far, or anything in regard to the amplitudes, the plots, or anything? Okay. So next, what we'll try to do, again, we could technically just ignore this first mode shape, but let's try to treat those washers as rigid, just to kind of I don't know, just to kind of avoid that issue. So there's a couple. You could either treat them as rigid, or you could just completely suppress them as well. I will say what I'll probably do. I'll probably go with suppressing them because I think that'll probably be a better example. I will say what would happen because I did actually try with them being rigid. With rigid, you still have the same mode shape one. It's just obviously the washers are not expanding; they stay the same size, but they still have this weird kind of like this weird coloration, like it's showing this high amplitude, although they're spinning around their own axis or something. But so that's one thing to do. So what we'll try here, let's go ahead and try just to suppress the washers out of this study. So what I'll do here is if I go actually back to my model here real quick, let me right click here and do collapse items just to kind of shrink that a little bit. So if we go to our configuration stats, I actually already have a configuration for washers removed. So if we kind of look in here, there are washers. And then what I'll do here is switch to our washers removed configuration. And yep, so we can definitely see that the washers are gone. So again, there's going to be a gap here, but again, since these are going to be constrained by the pin constraint anyway, and there's no contact constraints because they're not allowed in a frequency analysis, this probably wouldn't be too big of an issue. So I'm going to kind of copy this frequency 4, turn that into frequency 5, and kind of um, copy it with this configuration and try to run the analysis without the washers, and just let's see what kind of results we can get from that. So let's go here. And so obviously let me go and switch back. So one thing, if you select a study, if you've ever seen this where all of your stuff is grayed out, select a study and you're actually in the wrong configuration, you can always right click in the study and say activate SolidWorks configuration. And that'll just activate obviously the default, which is what we want in this case, because that's the one that was the configuration that was used to create this study. So the next thing we'll do is we can just go here, right click on this study, copy study, and we'll just call this frequency 5. We don't really need from frequency 4. So frequency 5, which is really from frequency 4. And when you copy a study, it'll give you the option to um, copy it or use a different configuration if you want to. So in this case, we actually do want to use a different configuration. We want to use the washers removed configuration. And actually, before I go there, I probably got a little bit ahead of myself. Um, for the washers can remove configuration, if you need to do this with the assembly, what you can literally do is just create a new configuration just by saying add configuration, give it a name, hit accept, obviously. It'll add a new configuration under here. And then what you'll want to do is then in an assembly, obviously, if you go back, let's say we're in the washers remove configuration, and I go back to the assembly here. So what you want to do is you just want to go to all the components. The washer is actually a configuration of the frame part. So all of these, the vertical, horizontal bracket, which the bracket is this one, and the washer are all configurations of the same part. I just did that just to make it a little bit easier versus having to model completely separate parts, since they all have very similar dimensions, the whole size is the same, and so forth. Um, so obviously the washers may change at a later date, but those can always be replaced. So one thing, so when you're trying to suppress something, just go to the assembly and suppress all of the different components. So right now, these are our main components, but then obviously we've got mirrors and we have a local pattern to actually pattern all of this around. So by suppressing this frame here, or the frame, which is the washer, and if you go to this one, it's obviously suppressed, you can't see it, but this is the washer configuration. Actually, I'll switch back to the default so you can kind of see what it will look like when it's unsuppressed. So there's our frame and it says spacer washer, same idea. So what you'll do is you'll just right click here and then do suppress. Now, for suppressing this one, is not going to suppress all the other ones. So what you'll end up having to do is go to the mirror components or whatever is using that one, and just make sure you go here and suppress all of these as well. Again, I'm not going to suppress them because this was already done in the other configuration. Some mirror components have 2 of them, so make sure you suppress both of those, and just kind of go through these. Some don't have any, which is fine. This one has spacer. This one has three of them, it looks like. So let's go through there. Also go through the local pattern or the linear pattern, which was used to actually pattern the floor and all these brackets kind of going up. So make sure you go through here. You got a whole bunch of spacers there. So go and suppress those as well. But that's kind of how you can create a configuration like that. So we'll go back and we'll go back to our washers remove configuration. I'll go and stop here for a second. Does anyone have any questions on configurations or anything that I've just talked about? Okay. So now that we have our watch and remove configuration, we can go back to here. Let's go and copy this study. So copy the study again. We'll get rid of this description after this. And we'll switch this over to washers removed. So, and when we go and hit accept, we might get a little bit of an error message because obviously some geometry has changed. Yeah. So since the geometry has changed, obviously the washers are not there. And if you recall, for our pin connections, one of the faces we actually selected was that inside face of the washer. So we're gonna have to kind of go through and just make sure we account for that. So we go into our connections, under our pins. So you'll see a few different pin connections that are affected by that. So one thing you can do here is you can literally just go right click here and just edit these. And if you notice, there used to be 4 faces. Now there are 3 faces. There's really nothing you really need to do here. You can just go into them and just hit accept, and that'll pretty much just fix that because it's looking for that face that's not there. It's not there. It'll just say we're not going to really even bother with it. So we'll just go through here and just kind of do the same thing. So we'll do that, hit accept, and we'll just kind of put those, so we're not having these errors anymore. So we'll go through there, and so there should be 4 of these in each group, so we'll have to do this about 16 times, or actually, we'll do it 16 times. So we'll do that, and come down here, do the same thing. The thing I can try to do, that does anything. Trying to do a control Q or force rebuild, see if that fixes anything. It does not. So yeah, sometimes you can try to rebuild it and it might do something, but in this case, since it's a simulation with connections and stuff, it probably won't modify those. So yeah, we'll just keep going down through here. Let's go here. And here. And finally this group. So we've got that. Let's see, hit accept. So definition. Again, this is where when you have a lot of connections or a lot of members, these studies can kind of get tedious. Not necessarily hard, it's just there's a lot of, especially when you modify something that's patterned, you're gonna have a lot of things you have to fix. 16 in this case is not actually too bad, but you can imagine if you have like 100 or 200 components, or even more, like 1,000 components, and you're trying to analyze something. Again, first of all, the studies are gonna take forever. Second, if you need to modify something, there's a lot of stuff to modify. So let me get out of here. All right, click here. Let me see if I can try to go down here. Yeah, we'll just try to collapse these. Okay, so we've got that. So now what we can do is our pin constraints now are fixed. Our roller and fixed constraints are still fixed, or sorry, are not fixed, are still good. We can still see the symbols. Obviously, those have nothing to do with the washer. So yeah, so we should be good now to go ahead and rerun our study again. So let's go here, and obviously since the geometry has changed, we're gonna have to remesh. So I'm just gonna right click here and just do a mesh and run in this case. There's really no need to mesh it separately since the parameters should still be the same. So we'll just give this a few seconds here to kind of run and then kind of see what kind of behavior we get. Okay. So now we have 2 mode shapes still. So let's look at both of them and kind of see what we're looking at here. So that's mode shape 1. Mode shape 2 actually I think is, yeah, actually in this case I think we only have 1 mode shape. The reason for that is the what's the word? Since we copied this, there were 2 plots before, so it's automatically going to try to add 2 plots even though there isn't one. So you can right click here and just delete. If we actually delete that, let's go to results again. Let's just do list mass participation. Yeah, we only have 1 frequency now because obviously the washers aren't there, and the washers were the only other thing that was really vibrating. So we've got our 82% now. Okay, so we have this. So let's go ahead and actually I won't even bother deleting that, but again, we can animate it. This is pretty much what was our mode shape 2 is now our mode shape 1. Or technically both of these are looking the same, but yeah, it's really mode shape 1. Any questions so far? Okay, so now what I'll try to do, we're kind of getting close to the end here, so I don't want to go too late, but try to get at least an hour in here. So what we'll do is, now what I'll try to do is, let's see, now that we got rid of our pin constraints and everything, let's go ahead and actually, or sorry, not our pin constraints, got rid of our washers. Let's see if we actually go and make these, the floors not rigid anymore. Let's make them flexible. So what we'll do now is, so we have this. So let's go and so I already have this here. I'm actually just gonna modify our frequency 4, and well, actually, yeah, I'm not gonna modify frequency 4. Let's just, I think I was gonna modify that one, but that's not actually gonna worthwhile. So let's go here, and I'll just go and copy the study again. So we'll copy this here. Again, this is going to be frequency 6 now. Again, typically, like you see on the bottom here, it's always good to actually give descriptive names to your studies. It never hurts to, so you can just kind of glance and figure out what's going on. Again, we want the washers removed configuration. So now we've got our pretty much our identical study here as frequency 5, but now what we can do is we can go under parts here and we can grab these and now make them, go and right click and make them deformable. And make sure that those are deformable, which they look like they are, so that looks good. And then what we can do now is we should just build one mesh and run. Technically, actually, we don't even need to mesh and run anything. We actually don't need to mesh. We just need to run. That's why the mesh is still intact because we have not actually changed any of the geometry. The only reason you need to remesh is like why we had to remesh between the first and the second time with the washers and the no washers is because now the geometry has changed. The washers were there and then the washers weren't, which means the mesh has changed. But when you haven't changed anything, changing something from rigid to deformable really does not doesn't change the geometry. It's just changing what the geometry how the geometry can behave, if that makes sense. So what we can do now is now we can just go ahead and run this study. And let's see what we get here. Obviously, we're expecting to get more frequencies now with the floors being deformable because now the floors themselves can vibrate as well. So it should be interesting kind of what we're looking at here. Um, again, our study's gonna take a little bit longer now. I think we're at 14 seconds. Yeah, we're at 14, 15 seconds now. Oh, it's actually not too long, a little bit longer. Okay. So we still only have actually one mode shape, which is actually rather interesting. Part of it is because of how low the frequency is. So what I'll do here, just to show, let's go to our properties here. Um, let's bring this up to like 200 hertz or something. Again, this is probably not really realistic, but just to show so we can kind of see some different behavior of the model if we kind of if we kind of up the upper frequency, I guess you could say. And let's try to just run this again and just see what we're dealing with. Um, so we can actually see. So this obviously tells us that the platforms being made out of ABS, which is our kind of pseudo PLA, just for this analysis, we probably really don't need to worry about them too much because most of the, um, what is it called? The frequencies obviously are not really in that range. Even at 200 hertz, we're actually not seeing. Well, let's see. Let me check here real quick. So I'm going to right click here and let's see how many frequencies do we have? Oh, we have a lot. Where are our frequencies? So you know what I'm gonna do to kind of limit this a little bit? I'm gonna go up to let's say 105 hertz, just so we don't have so many frequencies. Now we have 15. So let's run this one more time, but with let's do like 105 hertz, just to kind of see what some of the other frequencies are. So let's do that and do run. So once you have your simulation really set up, as you can see, it doesn't really take that much time to kind of modify and just kind of rerun the study. So if you need more frequencies or whatever, especially this feature is really nice if you to be able to just do it within a certain range, because then you really don't need to worry if there's like in our case with the earthquakes and stuff. A lot of the frequencies we're seeing were really, really low. Like some of them were like 5 to 10 hertz. So by having that low of a frequency, there's really no need to go up to like 1,000 hertz or 200 hertz. Even what we're doing right now is probably a bit of overkill, but I think it's a good um, kind of learning example. Because we have 7 different frequencies here. So now one thing, and let's see. So dominant is still our one, which is the one we have right now. So one thing here, I will say is it looks like we only have 2 frequencies here. So why is this the case? So I'm gonna go and delete this one out actually real quick. Um, and so sometimes if you have a lot of frequencies, depending also if you copy a plot or something, what you may have to do is you might have to go to results. You might have to actually define these other um, mode shape plots. Or so what we'll do here is I'll just go down here and I'm just going to go. So the first one was mode shape 1. This is going to be I want mode shape 2. So we'll go and hit accept. And I'll just have to. This is kind of a little bit kind of tedious, but I'll just go down here and try to add. I believe we had 7 of them. So we'll just keep defining them. And then we'll go back and actually analyze what they are. So let's go up to 3. And you can also just type 3 in there. So we'll do that. And let's do 4. Again, t by default, usually they have five, but since the first study only produced two plots, and then we copy that study, that's why it's only producing two. You can actually go into your settings and simulation and actually adjust this if you want more plots. So you don't have to do this. But if it's seven plots, it's not a big deal. Again, typically, if you have a certain frequency range, you're not going to have a tremendous amount um, of plots that you need. So there's five, two more to go. And this one's going to be six. Also, we'll tell you the frequency as well, which is nice. So there's six and seven. Okay. So I got those. Let's go and save one more time here. Um, so what we can try to do is let's see. So obviously our first plot, we obviously know what it's going to look like. It's the same one from before. Well, actually, it's a little bit different. So let's animate this one as well. So let's try to just go and animate, um, and see what it's going to look like. Again, actually, well, yeah, for the next one, I'm gonna stop. I think 15 frames is maybe a little bit too much because now that these are they're not rigid anymore, it's actually giving us a little bit more. Okay, so there's that one. So very similar behavior, but you can see that the floors are actually now able to deflect. So we'll do this. Let's just go down the list here. That's probably what we'll kind of wrap up after doing this because I think this is probably a good place to kind of stop. So let's go and stop here real quick. I'll just put this as 10 just to save us a little bit of. So it's a little bit smoother than 5, but we have saves a little bit of computational um, resource or a little bit of time. Okay. So again, this is occurring at 61, about 62 hertz. So in this case, obviously, we see just the floor. So everything else is not really going anywhere. The floors actually have their own kind of resonance here. But again, 60 hertz is more than we're probably going to be dealing with. But it never hurts to kind of understand where the frequencies are in case something maybe there's some other vibration that causes another vibration or something that vibrates a little bit higher. So we've got that one. Let's go down to 3. If you notice, most of these other ones are just about the floors. Um, so if you notice here that our dominant mode is still going to be the first one, which is going to be the entire building swaying. So that's really the one we're interested in. So this is where frequency analysis is really useful to um, just what is happening and where is it behaving the way you want and or the way you expect and you know where are some possible areas for further analysis. Because obviously if it was moving in a way that we wouldn't really expect or something, then, and especially with this, since we want to know what frequencies that, or what kind of mode shapes we're dealing with in our range of frequencies that we're going to be, trying to test once we actually build this model. So let's go and accept that. Let's go into 4. Let's see, I'm actually curious. I'll keep animating it, but so I'm actually curious if there's any others with the actual full structure, if these are all just floors. It looks like except for the first one so far, all of these have just been the floors pretty much having their own um, vibrations. So again, those are the floors again. So you can see again where rigid versus deformable can make a big difference because obviously by doing rigid, you're ignoring all of these other possibilities. So again, making them flexible is quite a bit more realistic. Let's go on to 5. And this is also the floors, it looks like. It's definitely also cool seeing all the different types of ways things can vibrate. Um, so obviously you can see that now we have like two, it's like almost like a double kind of sine wave here versus before it was just in the center. So now it's the edges vibrating. So it's kind of, doing that number. So really cool stuff. So you can see this area vibrating. So you can see the frames also vibrating as well, but obviously the mass participation is not huge in that case. So we've got that, hit accept. Let's go on to 6. And the floors again. You kind of see there's also, it looks like they're kind of mirror images a lot of times when you're animating it, like you have a first one first where one side might be high and then the other side is high, so the vibrations are um, they look very, very similar, just maybe mirrored about a certain plane. So let's see. This obviously is just the floors. Yeah, so very similar to the other one, but now it looks like maybe the other one is starting high, this one's starting low. So we have that one, and then last but not least, let's look at 7. And again, so we still just have the floors. So we'll do animate. It's also interesting to see that some floors, um, actually some floors vibrate and some others don't in certain mode shapes. So just because there's a certain thing and certain floors are vibrating doesn't always mean that every single floor is going to vibrate or every single component in the assembly is going to vibrate. Just because they have, or you can see this where these are vibrating quite these have a higher amplitude than these, although they're all made out of the same material. So these are obviously really, really good plots to kind of look at and just try to figure out. Again, most of these are like literally besides one, all of those could probably be ignored um, in our situation. But it's always kind of good to look at it and just figure out, what parameters is my system, structure, machine, whatever, going to be under, and what kind of vibration modes should I be expecting? And based on those are the ones you really, really want to focus on. Again, most of the stuff, the research we've done for earthquakes is usually about under 20 hertz by a lot of times a lot. So like 5 to 10 hertz. So these ones that are up at 60, 100 hertz, whatever, are really going to be way outside of that thing. But it's always fun to kind of up it a little bit and see what other possible vibrations there are. Any questions so far or anything? Okay, so let's see here. So I think that's probably good for today. I think that's probably a good. Hopefully, this is everybody kind of understands this. I think it's probably a good exercise for kind of linking together probably the prior 2 sessions, or at least the prior session, for kind of so more of a real life example versus kind of a more of just a classic example of something that you might learn in a class. This is more of kind of some of the applications you could use this type of thing. Um, and again, typically frequency analysis is not something, or even connections, is not something that's actually taught in computer-aided engineering or CAE. For those of you who haven't taken the class yet, you're actually probably seeing stuff that you probably wouldn't even see in the class. But you can definitely see that there are cases where these can be very, very useful. Um, so yeah, hopefully this was, informative and everything. But yeah, if there's no more questions, I think this would probably be a good place to stop recording. So any questions or anything? Okay, so let's go and stop recording here.